going to talk about information-theoretic techniques about many-body physics, and I hope he will not play the same trick as Thomas and only talk about two-body physics.
Thanks, Harry. So thanks for still being here. I want to continue where I stopped yesterday. So yesterday, right, I talked about how. So the main topic of yesterday and today is about entanglements in ground states, right, in the lowest energy states of many-body Hamiltonians. And yesterday we talked about how, in some circumstances we can just forget about the entanglements completely and just use product states as some ansatz for getting, like, calculating the minimum energy, for example, and how this works well in some situations. And the main point was that information theory was useful in seeing when, like, product states do a good job, right? And information theory was really the basics of information theory, right? We didn't use anything more than, like, definition of entropy or mutual information and some of the basic properties, right? So we only use information theory in some abstract way, if you want. So today I want to consider a more restricted class of systems, just one-dimensional Hamiltonians. But the advantage of doing that is that we will be able to address the entanglement in these ground states in a more sophisticated way. So instead of just considering product states, we will consider some more interesting ansatz for these ground states, which are called matrix product states, and I'll get to that. And these states, they're very special and they're very useful. So, for example, they're connected to interesting properties like area law and exponential decay of correlations that I will also tell you what they are. And the main point will be, again, to see how, using information theory ideas, we can understand better these states, right, and their properties. And what's interesting is that today we're really going to use more advanced themes of information theory, right? So, like, more recent results in quantum information theory, like state merging and decoupling, and I've just mentioned the end also that we have to use some single shot protocols, but I will leave the details to Nilanjana's talk tomorrow. Okay, so again, the same slides, right? So we have a quantum Hamiltonian. It's just a sum of local terms, like here. And today is right? We just consider on line. So this is the situation we're considering. There's a bunch of spins. Can be d-dimensional. I will just consider qubits for simplicity. And then we have some interaction here, nearest neighbors or next to nearest neighbors and so on. And we like to compute properties of this model. And I'll be interested in computing properties at 0 temperature. So really in the lowest energy eigenstates and its properties like correlations or energy. So what can we do? So again, there was this problem about approximation scale, right? So maybe you're interested in computing the minimum energy, just this minimum eigenvalue. But maybe to compute it exactly is difficult, but you can approximate it. And yesterday we talked about small extensive error, right? Because this is what we could say something non-trivial for these more complicated Hamiltonians. Today, because we have a simpler situation, we'll be interested in really getting approximation to the total error. Okay, so really computing the minimum eigenvalue up to some small additive error. So again, yesterday was about using product states as some ansatz. Today is about using a different class of states, which are called these matrix product states. So these are really nice states. They were introduced in 92 by Fernando Brandao and Werner. And you can think of them as states. So this is just some general states on n qubits. And you could write this state as some, writing in the computational basis, for example. And then if you would just write in the computational basis, instead of having this trace here, you would just have a n indices tensor, right? So n index tensor, which just gives the coefficients of this state. Now, a matrix product state is a particular kind of state where this tensor can be written as a trace of product of matrices, right? So to describe the state, you have many matrices. So for each site, like for the first site 1, for example, you have 2 matrices, right? Because it's qubits, and then for the second you have 2 matrices again, and so on. And these matrices, they cannot have arbitrary size, but they are d by d matrices, okay? And if we can write the state like that, we say the state is a matrix product state of bond dimension of d. So this d is just some internal dimension, right? It's not on the physical space, but just tells the complexity of the tensor. So why this is an interesting thing? Why it's useful when we can write a state in this form? Because first, we can describe the state just with a few parameters, right? So if you want to describe a general quantum state, we need exponentially many parameters, right, in the number of spins. Here, if we just count how many matrices we need, we can describe with n number of spins and d square parameters. So moreover, this is actually a good ansatz because we can compute things that are interesting to us. So given this guy, given these matrices, it's very efficient to compute like local expectation values. For example, the energy, right? Suppose you're given this and you want to estimate the energy. Then you can do that efficiently. So even if you actually look at what people do in practice, like in condensed matter, when they want to simulate these one-dimensional systems, they use this DMRG, like a density matrix normalization group is a very useful thing. And it's really just some variational method over this class of ansatz, over matrix product states. So they perform, so this seems to capture what's going on in one dimension, right? It works very well in practice. And it's nice because it's a way to go beyond product states, right, that we saw yesterday. So if you just look at this state when the bond dimension is 1, you can just check that you get product states. Then you can start growing and putting more complexity ground state, up to the point when this capital G is exponential in n, like 2 to the n, then you can actually write any state like that, right? So it's just a way of interpolating between product states and general states. But of course, we're only interested when this is sufficiently small. Any question on this matrix product states? Okay. All right. So one property that that is interesting on itself, but is also very related to this class of states, is area loss. So area law in one dimension is the following property. Suppose we have our chain here of particles, and then we split into two big chunks, x and y. Then we can see how much entangled x is with y, right? And because it's a pure state, it's pretty easy to measure entanglement, right? We should just look at some entropy measure of the reduced state, right? So for example, look at the state on row x, and we compute either the von Neumann entropy or some other entropy, right? And the more mixed the state is, the more entangled x is with y. Okay, so for example, if this is the von Neumann entropy, we would expect that usually the amount of entanglement scales with the volume of x. We say that the area law holds if this is not the case, and the amount of entanglement only scales as the boundary of x, which is constant here, right? The boundary is just here. So whenever we have this state for which it doesn't have a lot of entanglement, the entanglement is just constant. In any cut that you choose, we say that the area law holds. Okay, so this, area law has been studied like in connection with black hole physics since '73, and there's a lot of research on spin systems, and there's a review if you want to check there. So it's it's an interesting property of these systems, but just to remind you to switch off your bye-bye. Sorry. For just a second.
Who is it?
Terry Rudolph. Creating problems, yeah. So this area law is, sorry about that. So this area law is relevant here because it's tightly connected to these matrix product state representations. So, sorry, I missed something important here. Yeah, what this picture means, right? So we can write in the, like an equation like this, but there's also some nice graphical way of writing these states and thinking about them. And you can think about them, suppose these are the sites of the model. Okay, so this is the first site, this is the second, and so on. And you can imagine that these states are formed by putting like virtual particles inside each site, two of them, like these, the two virtual particles of the first site and these of the second, and then connecting the sites by maximum entangled states of dimension d, this bond dimension, and then just projecting this with this matrix on each site. So this matrix, right, just maps this d by d space into 2, right? Because this I just goes from 1 to 2. So you can think it's just that you have a lot of maximum entangled states between nearest neighbor sites, and then just project them to get these states. And if you just do the math, you contract everything, you see you get this state. So the details are not very important, but what's useful here is that the entanglement structure is pretty easy, right? So this projection that we are doing here, you cannot change like the Schmidt rank of the state, right? So this doesn't change the entanglement too much. So the entanglement really is only coming from this maximum entangled state here, right? So what this says is for a matrix product state, if you look at like this S max, which maybe Nilanjan will talk more about, but it's really very easy, just the log of the rank of rho x, okay? So the number of log of the number of non-zero eigenvalues. Then because of this construction, this is always smaller than log d, right? So if this constant, this state satisfies area law. This is what this is saying. More interesting, the opposite is also true, actually. So, and this is already in the original paper, then was rediscovered by Vidal, and there's a nice way of seeing this in a review paper by Richard Joseph that I recommend if you want to learn about this, how you do it. So it says that if psi is such that it's just some states on n qubits, and it's such that for all x, S max is bounded, is more than log d. Then you can find a MPS description of bond dimension d. Okay, so like there is some equivalence between in one dimension between matrix product states and area law. And if you want to put some epsilons, maybe this will be useful, and it will be useful later. It's still true, even if psi, S max is log rank. Maybe you want to allow some approximations there. You can use the smooth version of S max, where we just minimize over all states which are epsilon close to rho epsilon, the S max of rho epsilon. Okay, so you just average around rho S max, and then even if this is small, then maybe there is not exactly a matrix product state, but still the state can be approximated by a matrix product state of bond dimension d up to arrow, or this is wrong, should be epsilon times n. Okay, so for this to be useful, epsilon has to be pretty small, like smaller than 1/n. So it should be n here. Okay, so that doesn't matter too much. We don't want this later. What I would like to tell you is this equivalence, right? So area laws are interesting because you can, if you have them, then you have this kind of parameterization which is very useful. Any question?
What was the n you mentioned?
Yeah, 0 should be epsilon times n, actually. Oh, n is the number of particles, number of spins. Okay, so this is one property of matrix product states. They relate to area law. Another property of these states, of these many particle states, that is connected to, yes.
Can you just follow up on this? Is n the number of particles you trace out, or the total number?
The total.
Total.
Yes. So another property that will be related to matrix product state is what we call exponential decay of correlations. So let me show you what it is. So here again we have our state on n particles, and now we divide into 3 regions, okay, x, y, and z. And then we can see how much correlated x is with z, right? So like yesterday we were using mutual information, right, between x and z, and you could use that. But it's difficult to usually given a physical system to tell that mutual information there is small. There is some other weaker forms of correlations which we can say more about in typical physical systems. And one of them is this correlation function. So this is the definition. So you just, it's correlation between x and z, you define like that. So you consider the reduced state, rho on xz, you trace out y, versus the reduced state on x tends to the reduced state on z. Okay? And then you just compute the trace of this difference with some any operator which is tensor product of some anything on x, m, and anything on z, n. Okay, so this m acts non-trivially only on x, and this n only on z. So like if it's some generalization of 2 spin correlation functions, right, where you can measure a block of sites here and a block of sites here. And then we say that the correlations, they decay exponentially if there is some constant, psi, like the correlation length, such that doesn't matter how we choose these 3 regions, if y has L sites, the correlations between x and z, they're exponentially small in L. Okay? And how small, and this in the exponent we have this psi. Okay, any questions on this? So when the state satisfies this, we will say that it has exponential decay of correlations. Sometimes people also say there is like the clustering property. You also find this. But again, what's interesting here is the connection of matrix product state with exponential decay of correlations. So what is known is that matrix product state, if you have an MPS, then this, up to some caveats that I'll tell you, implies exponential decay of correlations. Okay? So let me briefly show you how this is done. The details will not be very important either, but let me just give you a flavor. So suppose you have this matrix product states, then there is actually some freedom in this matrix. You can choose many different matrices that give rise to the same state. And in fact, you can always choose them to satisfy this condition, okay, for each j. But then this just shows that, right, you can think of this AJ0 and AJ1 and AJ2 just as some unital channel, right? So it preserves the identity. And this is the channel associated to this site, right, this epsilon. Now, this is a channel and it's unital. We can look at the second largest eigenvalue, right? So the largest eigenvalue is just 1 when you put identity here. The second largest eigenvalue, let's call it lambda j, okay? So we could compute it. So it can be 1 again, but it typically will be smaller, right? And then we just look lambda is just the maximum of lambda j, where j is the second largest eigenvalue of this guy. Now, an interesting class of matrix product states is when this lambda is independent of n, of the size, okay? And this is the matrix product state that would be interesting in, actually. And then we can call them GMPS, like gapped MPS, right? They have this property. And this gap, this lambda is interesting because if it's non-zero, then they say it has exponential decay of correlations. And the correlation length is some function of this lambda, this one, which don't worry too much. But so the thing is that, we have this channel associated to the matrix product state. Whenever there is a gap there, which in many situations we will have, and I'll give you some examples later, then the state has exponential decay of correlations. But the direction is, as far as we know, is from MPS to exponential decay of correlations. And later we'll see whether we can have the other one as well, but we'll get there.
Fernando?
Yes.
Normally when you talk about gaps,
Yeah.
you talk between the lowest and the...
Oh yeah, indeed. Here's between the largest and the second largest. Yeah. No, because it's not a gap of so many body models. It's just a gap of the channel. Maybe I shouldn't use gap. It's just the difference. It's just the value of the second largest eigenvalue. Okay. Yes.
If it's unital with only 2 cross operators, why would lambda be smaller than 1?
What do you mean? No, because this guy has many eigenvalues, right? Because these matrices, they are d by d, right? So it's like computing the eigenvalue of this matrix, right? And the same thing for 1.
That's a plus in the middle?
Plus, thanks.
But so one issue is that maybe that matrix isn't even Hermitian.
That's true. That's why it can be complex, but we look at the absolute value. Yeah. That's true. Yeah. So what matters is the absolute value. But your question is why it has, if I only have one eigenvalue, or?
Well, I may have some confusion about what the dimension is here.
Oh, okay. Yeah. So right. So each one of these matrices is d by d, and you have 2 of them. Yeah. Okay. Okay. So this is just to motivate this MPS and tell some of the properties, but are they good, right? So yesterday we were seeing whether product states are good when they are good, and here we can ask the same thing for MPS. And there's some negative results actually. So probably Daniel will tell more about, but first, they can be hard, like from computational complexity point of view, can be QMA hard, even when you have some translation invariance. But more to the point, actually, you can just construct models for which the ground state doesn't have a good MPS description. Okay, there's like volume law, volume scaling of entanglement, and then this MPS will do a bad job. So in general, there is no hope that they can approximate any one-dimensional model. But there is still hope because there is a very interesting class of models for which they actually do a good job, and it's these gapped models. So Toby already explained to us yesterday, right? So we have a Hamiltonian. We can define the spectral gap. It's just the difference of the first excited energy. So the second, so the minimum eigenvalue and the one above it, right above it, right? So this is the gap. So actually, if you think about a gap, you can think about a family of Hamiltonians where n grows. And if this Hn is gapped, then we just mean that when n grows, this is always bigger than something independent of n, some delta, which is independent of n. And whenever that's the case, right, there are many interesting, models with this property. Then, we usually when this happens, we are far away from criticality, so we expect that maybe the ground states are simpler or something like this, right? And so this is just some intuition, but indeed it's true. So there is a lot of very nice results that just connect ground states of this class of gapped models, far away from criticality to a number of interesting properties. So this is like work by Hastings from some time ago, and more recently by Arad, Kitaev, Landau, Vazirani, and Landau, Vidic, Vazirani. So first, if we have a ground state of a gapped Hamiltonian, there is area law. Okay, this was proved by these guys. Second, if there is ground state, if it's a ground state of a gapped Hamiltonian, we also have exponential decay of correlations. Correlation length goes like 1 over gap. So what these guys show, even if you have a ground, a ground state of a gapped Hamiltonian, also the ground state has, is well approximated by MPS, and you can even find this MPS efficiently. Okay, so once we know it's a ground state of a gapped Hamiltonian, we know a lot. It gives a lot of structure. And this really shows that these matrix product states are very useful there. But, okay, so they use a number of techniques, like more analytical or more combinatorial. There isn't much information theory there, actually. A little bit in this Hastings, actually. We'll see that later. But, just to get some information theory in this problem, let me just ask some different question, right? Which in a sense is trying to get rid of the Hamiltonians, right? So we just want to talk about quantum states. And the question is, we just saw, right, that if we have this class of MPS with this gap, they always have exponential decay of correlations, and they always satisfy area law, right? So the question is whether we can put some more arrows in other directions. So, and if you want some physical motivation, maybe there's this like gapless Hamiltonians with no gap, so the previous result doesn't apply. But they have, they're disordered models, so they have like mobility gap, or people call dynamic localization. And it's known that under this, like other kind of gaps, which is not a spectral gap, we also have exponential decay of correlations. And like there's some recent papers on that. So maybe it would be interesting to see whether, what we can say just by exponential decay of correlations. And this is the result I want to tell you, is this one. That from exponential decay of correlation, we can also go, show that there is a matrix product state and show an area law without any Hamiltonian. So it's just a property of states now. And this gives this, this equivalence between these two class of states, which I think is nice, right? Tells us, tells us more about this class of states, right? Just that it's equivalent to this maybe more natural class of states a priori. Any question? Okay. So what I want to do in the rest of the talk is just that, okay? Try to explain this one. And actually this one we will actually follow from showing that exponential decay of correlations implies area law. Okay? So first, let me give you some argument why it's very natural to expect that this will happen, that we should have area law from exponential decay of correlations. So the argument is the following. Suppose that, again, we have our line. We have x, y, and z, and y is of order correlation length, a little bit bigger. Then, if the state has psi exponential decay of correlations, right, the correlation length is psi, the correlations between x and z should be very small, right, should be epsilon. So in some sense, this rho xz is close to rho x tensor rho z, right? But if it was not close, but it was exactly equal, we would be in good shape, right? Because then by Ullmann's theorem, this would just imply that actually we can see this state as just a state pi between x and some subsystem of y, y1, and another entangled state between z and a subsystem of y, y2, up to some isometry mapping y1, y2 to y, right? And therefore, this shows that X would just be entangled with Y and Z only entangled with Y. So because Y is not so big, this gives the area law. So any question on this argument? I think probably we'll hear more, maybe Nilanjan will talk more about it. So it's very, this kind of a decoupling argument. I'll tell you more later, but it's very central in like quantum information theory. So this is nice, but it doesn't really work here. And the reason is because I was very a bit misleading here, right? I just said that they are close, but they're close in the wrong sense, right? So to apply Ullmann's theorem, we can apply when they are just close, but we need one norm. We need trace distance, right? So if actually rho xz was close in trace distance to this product state, this would work. But it's not the case, right? So, and why is not the case? Well, trace distance we can write like this, right? We can maximize over all P of M's, M, acting on A and C at the same time, rho AC minus rho A tensor rho C. But what we have is weaker than that, right? So what we have is just M of the form X tensor Y. This is what we have in exponential decay of correlations. And this M might be something global. So we cannot say anything about the trace distance, in principle at least. Any question? Okay, and well, but maybe this is just a detail, and right, we can maybe just massage this and things would work. But actually, it's not the case, and there is a very good reason why it's not the case. And it is this data hiding states. So these are the states which you can distinguish them very well globally. But if you just have access to these local measurements, like we have for correlation function, right? We just measure something locally on X and something locally on Z, then we cannot distinguish them at all. So one example, striking example that Aaron already mentioned in his talk is this antisymmetric Werner states, right? So have identity minus swap, this is the flip, and normalized. You can compute the correlation function between them. Well, not compute exactly, but you can bound them pretty well, and it's always smaller than 1 over dimension, where it's a d by d state. This is the local dimension. On the other hand, you can compute the one norm between the states and the reductions. And then you compute this roughly half. So you see there is this huge gap between correlations that you see by local measurements and correlations you see by global measurements, right? They're just not related in general. And therefore, this Ullmann's theorem, it will not work here the way we want, right? And even random states, you have the same kind of examples, but so correlations will be very small, but you might have volume scaling of entanglements. Okay, so because of data hiding, this intuitive explanation that I try to convince you it doesn't work, right? And maybe it could be that it leads to a no-go for area law from exponential decay of correlations, but it's not quite true because we fix a partition to get this difference between local correlations and global correlations, and exponential decay of correlations gives us more, right? We have really this small correlation in any partition we choose, so we can try to explore that. So what I think is interesting is that it really shows that this problem of area law from exponential decay of correlations, even if you forget about physics, is still interesting, right, from an information theoretic perspective. It's just we want to understand data hiding better in these quantum states. So this is another motivation. So let me tell you the results that I want to show you how you can prove it. So it says what I mentioned before, right? That if you have a state psi on n qubits and it has psi exponential decay of correlations, then it doesn't matter how the size of x, and m can be any parameter, then this smooth max entropy will be small, right? So it will be something that only depends on the correlation length exponentially here, plus this m you can choose. So this m just gives a trade-off between the error here and the price you pay. Doesn't matter too much. So for example, if you this version is stronger than just area law for von Neumann entropy. Okay, this one. So in particular implies that, but this is useful because this actually implies that there is a matrix product state approximation, which I mentioned before. So it's only valid in one dimension. That's unfortunate, but it's, seems that it's very hard to go beyond that. And it reproduces this bound of Hastings for ground states of one-dimensional gaps Hamiltonians, right? Just because, as I mentioned, such states have exponential decay of correlations. And the dependence will be the same. So in this more recent work by Arad and collaborators, they can improve this dependence for the case of ground states. We don't know how to do this here. Like, maybe get some linear in the correlation length, could be, but we don't know. Any question? Okay. Okay.
What is omega n?
Sorry?
What is omega n in the exponent?
Where is omega n? Oh, omega n. Ah, here. Oh, sorry. It just means like some constant times m.
Oh.
Okay. Right. Okay. So, well, this is what I said. Just repeat. So, a corollary is that if it has psi exponential decay of correlations, for every epsilon you choose, there is this like gapped matrix product state psi epsilon with bond dimension not so big, polynomially in n and 1 over epsilon, which gives a good approximation. Okay. So, yeah. Right. So this is the result. Now let me tell you how we can use information theory to prove it. So before outlining the proof, let's consider some toy example that will teach us something useful about this problem, which is like random states. So suppose we pick this state on n qubits at random from the Haar measure, like here. Then you can compute things, and you can see that if the size of x is like approximately the size of z, then the correlations between x and z will be exponentially small the separation. Okay, under this solution. And you can also compute, and the entanglement of x, so entropy of x, will be roughly the entropy of z, and almost maximum, right? So so the size of x is n minus L over 2, and likewise for the size of z, but roughly, but the entanglement will be very close to this maximum value. So this just, again, what I mentioned before, small correlations in a fixed partition doesn't imply area law, right? Here's like volume scaling of entanglements. But as I already mentioned, we can move this partition, right? And maybe we should just choose a different partition and see what we get of these regions x, y, and z. So let's choose this partition now. Let's choose x roughly the size of y, but such that both of them is much smaller than z. So z is this huge region now. Then again, you can compute things because it's a random state, so you do some calculation and you see that the states on x and y, the reduced states, is very close to the maximally mixed states. Okay, so very close to these states, up to some error exponentially small in n. So when this happens, right, when we have states which are very close to products in trace norm, we say that x is decoupled from y, right? And I'll tell you more later about this decoupling. So what this shows is that we have indeed this extensive entropy, right? The entropy of x and entropy of y, is like volume scaling. But maybe we shouldn't care, right? Because of this decoupling, now we can actually apply Ullmann theorem in the right way, right? So this just shows that x is maximally entangled approximately with some subsystem on z, and the same thing for y, right? Because this is a particular purification, two states close to maximally entangled between x and a subsystem of z, and between y and a subsystem of z. And we know they are approximately related by some isometry, or x on z only. So it shows that the correlations between x and z, they are of course bigger than the correlations between x and the subsystem of z, z1, and it's a maximally entangled state, right? So they are of order 1. And then, well, this just shows that we have long-range correlations here, actually, right? X and Z, they are separated by L, but the correlations are still constant. So there's no exponential decay of correlations here. So, okay, maybe this is boring because why we care about these random states if they don't have exponential decay of correlations? But what happened here gives the hint for the idea we should explore, right? So for the general proof, what we try to do is to show that large entropy leads to large correlations by trying to mimic what happens here. So what happens here, what was nice is that the entropy here of x and y, it was so large that actually the state has to be close to maximally mixed, and this leads to large correlations by decoupling. Usually we won't have this situation, but we can try to get close to the situation by first making a measurement on the region x and try to decouple it from y. So the strategy would be this one. So any state that we're given, we make a measurement here on x, to try to make it the post-measurement state close to product with y, and then we try to see that if we can do this in the right way, there will be correlations. If the entropy of y is sufficient, of x is sufficiently big. So let me be more precise about it. So what we want to do is do entanglement distillation by decoupling, okay, which is something very useful for information communication and so on. But here we want to use this as some tool to analyze the correlations in these states. So let me show you the information theory that we're going to use. So suppose we have Alice, Bob, and Eve, and they are in the pure states, A, B, E. And now suppose that Alice wants to distill EPR pairs with Bob. Okay, so she wants to make some local measurements on her system, then communicate some classical bits to Bob, and in the end they want to share EPR pairs. Then of course it's very interesting to derive protocols for this task, right? And we have some nice protocols, for example, this state merging protocol. So let me show you what these achieves. So given psi, ABC, should be E here. Yeah. Alice can, so what the protocol shows is that Alice can distill this number of EPR pairs with Bob. So minus the conditional entropy, right? We call coherent information this. It's just the entropy of B minus entropy of AB. So she distills this number of EPR pairs with Bob. If she makes just a random measurement on her system, where she just chooses some basis from the Haar measure and measure, but just grouping together some of the outcomes, so the P of M, the projective measurement, just have this number of outcomes, of elements, so exponential in the mutual information between A and E. So this is the expression for mutual information we saw yesterday. And so she makes this measurement and she communicates the outcome to Bob, right? So she makes these measurements with this number of elements, communicates mutual information of A with E bits to Bob. Then Bob does some decoding, and in the end, they have this number of EPR pairs. Okay? So actually, if for this to actually work the way I said, we have to use many copies of N. Okay? So let's forget about it for now, and suppose this works for one copy. And then see later how we address this problem. So just some equations to the state merging works by applying this random measurements. These are the measurement operators pk to A. And the way it works is that we just apply this pk to A such that we try to decouple A from E. Okay. So this after the measurement psi gets mapped to some phi, which is just proportional, right, to applying pk to the A part of psi. And what we can show is that using the numbers like that, the post-measurement state on A and B will be close to product, right? So it will be close to a maximum mid state on A here and the original state on Eve. So now Alice is decoupled from Eve. But that's nice, right? Because if they are decoupled, Bob has a purification of both of them. And because the reduced state on Alice is maximally mixed, they will have these EPR pairs. So what matters is the rates here for us. So if you just look at the number of pKs, right, the log of the number, this is mutual information of A and E, as I mentioned before, and the number of EPR pairs, which is just the log dimension of this, it should be A, of this A system, is the coherent information. Any question here? Okay, so, right. So maybe this is complicated, but now we can just forget about this information theory and just use it as this lemma, right? So this kind of expression will be what concerns us. So this just is kind of the direction of what we want, right? It's a relation between saying that if entropies satisfy something, then correlations satisfy something as well, right? And the direction that if the entropy of Z is bigger than the entropy of Y, then actually the correlations between Z and X, which is far away, is also bigger than something, right? So this, and these are already hints that maybe this is useful for area law, right? Because suppose you want to prove an area law for Z. So one way to prove is just to show, well, we want to show that the entropy of Z, which is this big region, is always smaller than the entropy of Y. And they say, well, suppose it's not the case, then we are here. But then the correlations are bigger than something, right? And if you can show this violates the hypothesis of exponential decay of correlations, it would work. Okay, why we have this? So we can rewrite this like that, right? So entropy of Z entropy of y is equal to the entropy of xz, because it's a pure state. So this is exactly the APR pair distillation rate, right, of the protocol. So if this is bigger than 0, it means that you can distill at least one APR pair. But now we make this random measurement on x, right? And in this correlation function, we cannot communicate anything. So we really have to post-select on a particular measurement. But each measurement only happens with very small probability, right? So we have to pay the price for this. And the price, because they are random, they all are equally likely, and the price is exactly 1 over the number of them, which is this one, right? So the protocol is really like Alice makes a measurement, post-select on a particular outcome. Now they have a APR pair, but this measurement only happens with a small probability. So APR pair has constant correlations, but we have to multiply by the probability of making the measurement on Alice. Okay, and now we can just try to explore this relation, right, between entropies and correlations. Any questions here? Okay, so what's the proof strategy? The proof strategy is to use this, this lemma that I just showed you in 3 steps. Okay, so one is that in the first step we want to get the area law from exponential decay of correlations under some assumption that we made that there is a region of sub-volume law. So here is a boosting argument, right? We want to go from a region of sub-volume law, so not the maximum value of entropy, to something that has an area law. So this will be one argument. Then we want to relax this assumption in the second part. So we show that we can actually get this region of sub-volume law that we need for the first step. From another assumption, there is a region of small mutual information, and I'll show what this means precisely, right? And finally, we show that there is always a region of small mutual information. So from this one, from small mutual information, we get sub-volume law, and from sub-volume law, we get area law. This is how we do it. Okay, so let's show this. Let's see this first step, right? So this is the result that I showed you before, right? If the entropy of z is bigger than the entropy of y, the correlations between x and z, they're big. We can go to the reverse direction, right? So, right, this is the same as this one, right? If the correlations are actually smaller than that, then the entropy of z is smaller than the entropy of y, which is in the right direction that we want. So let's use our assumption. Our assumption is this one, is that the entropy of y is smaller than L over 4 xi, right? So y has L qubits. So the entropy of y can be at most L. So we just assume that it's smaller than the maximum by some multiplicative constant that depends on the correlation length. This is like the sub-volume law assumption, right? Well, this is even volume law, but this constant has to be small enough for us. So okay, let's show how this implies area law for z now. So the mutual information between x and y, we know, right? It's a basic fact that it's always smaller or equal to twice the entropy of y. I mentioned this yesterday, I think, but there's this 2 because it's a quantum state. By assumption, this guy is smaller than L over 2 xi, right? Just by the sub-volume law assumption. But the state has exponential decay of correlations. So the correlation between x here and z is smaller than 2 to the minus L over correlation length, right? But by this equation, this is smaller than 2 to the minus mutual information between x and y. Good, but then we are here, right? So because the correlation between x and z is smaller than this term, this implies that the entropy of z is smaller than the entropy of y. So if y was not very big, right, if this L was a constant, this gives area law for z, right, because this is independent of the size of z. So this is the first part, right? So we just use exponential decay of correlations and this thing that comes from the protocol for entanglement distillation. Any question? Okay. Right, but how to get rid of this assumption, right? Here we want to get the sub-volume law that we needed from another assumption that there is a region of small mutual information. Okay, so now the situation we consider is the following. Suppose that we have like 4 regions. One is the outside here, then YL, Y central, and Y right, and then suppose that the central region has L sites, and the boundary ones has they have L/2 sides. Okay, and now what we want to show, the assumption that we want to make is that the mutual information between the central region and the neighboring ones, the boundary ones, again, this could be at most L or 2L, right? We want to say that it's sufficiently smaller. It's like L/4 correlation length. So a little bit smaller than the maximum, and this will be our assumption now. And what we want to prove is that this implies, this and exponential decay of correlations imply that the entropy of this YC, the central region, is small, has like the subvolume law. And again, it will be just basic things. So we have exponential decay of correlations, right? So we can look at the correlations between YC, which is the central region, and the rest, which is here, right? So now YC is like, you know, in the protocol was Alice, and Bob is this region R, and Eve will be the boundary ones. So exponential decay of correlation implies this, right? Because the separation is L/2. So we have this bound. But by our assumption of small mutual information, this is always smaller than that, right? But again, we can use our lemma, right? So so the mutual information between Alice and Eve, the correlations between Alice, which is the central region, and a faraway region R, is smaller than the mutual information between Alice and Eve, the neighboring ones. Therefore, the entanglement of, the entropy of R is smaller than the entropy of the neighboring ones, of Eve, right? This is what is here. But the entropy of R is equal to the entropy of all these three subsystems, because it's a pure state. And therefore we have this relation here. And then that's it, right? Because this entropy that we are interested in is smaller than this entropy plus this term, which is bigger than 0 by this equation. But this is just a mutual information, right? That's a mutual information between the central region and the neighboring ones and the boundary ones. But by assumption, this is smaller than L/4 side. So we have the subvolume law, right? The entropy of the central region is smaller than this term. Okay. So again, this exponential decay of correlations and this new assumption that we have. Right. So what this implies? This implies that if we can find this region of small mutual information, then we have an area law, right? So to prove an area law for Z, which is the original region we want to prove it, it's sufficient to find some region which is not too far away and is not so large with these parties, which has small mutual information. And we show that we can find this where not so far, not so large is exponential in the correlation length. Okay? So why this is true? Why it's enough to find this region? Let me show you. Suppose we have Z, which is the region we are interested in. And now suppose that for some reason, that I'll show you next, we can find this region, YL, Y central, and Y right, which is L far away from Z. Okay? But now this region has a small mutual information. Right? This region satisfies this equation. So by part 1, the central region has subvolume law, right? Satisfies this equation. But by part 1, then Z prime, which is the extension of Z, right? Because for part 1 we needed that the subvolume law region is neighboring the original region that we're interested in. Then this entropy of Z prime is smaller than that. But these two regions, Z and Z prime, they only differ by the factor of L. So the entropies cannot change too much, right? So we can use standard things for entropy, and we get that finally the entropy of X can be at most something exponential in correlation length as well. So all that we have to do now is to prove this, right? That given any point here, like that, this boundary of Z, we can find this region with small mutual information and far away at most by this factor. And this actually, luckily, this in some sense already in this original Hastings proof of area law. So he didn't formulate like that, and that was the only information-theoretic part of his proof. But this turns out to be useful for us in this approach here, and I think it's a nice result, because just thinking about information theory the way we like to think, where where each part is very well defined, I don't think we could come up with this kind of statements. So it's something where the size of the parts is vary, is not fixed, and then this leads to some interesting new distribution statement about how correlations are distributed here. So just to finish, I won't tell you the proof of this. It's actually very simple once you formulate, but I just want to tell you what's the statement, and maybe it's useful for something else. So the statement is the following. So suppose you have a region X and you're given a size S. Then for any epsilon you choose, you can find some free regions, right? Y, L, Y center, Y right, as we want. And the size is as we want. Here is 2L. Here is L. And for right is L as well. And this L is at most something exponentially big in 1 over epsilon. The distance is also bounded. Is at most, this distance is at most exponentially in 1 over epsilon. And the mutual information is small, right? The mutual information between the central region and the neighboring ones is smaller than epsilon over n. Okay? And this works for any state. Any probability distribution is, right? It's something about correlations only. And it sounds surprising at first, right? Because how can this happen? Maybe how can we have something so general? But it's really because we can change the sizes, right? So you say, well, maybe we choose a region and the mutual information is very big, right, between this guy and the neighboring ones. But then for that to be the case, you must have a lot of entropy here, right? Or a lot of entropy here. Then we can just choose a smaller region which is all inside here. And if the global state has a lot of entropy, mutual information has to decrease a little bit. And you keep doing that. You keep changing the region and the size until you find one where epsilon is as small as you want. So it's just some statement about how correlations can be distributed, right? They cannot be big on all length scales. And that's exactly what we need. So if you look at the proof, we just use subadditivity many times of entropy, and that's all. But I don't want to show you. Okay, so that's also just to mention. I was using this assumption that we can just use asymptotic information theory, right? We can use entropies and mutual information, all Shannon or von Neumann, which only really works when you have many copies of the state. But we only have one copy of the state in this problem. So this sketch that I show you doesn't really work, and we must use single-shot information theory, right? Which Nilanjan will tell you what's about. So this addresses exactly this difficulty that we have here. We want to use information theory and entropies, and it's useful for us, but we only have one copy of the state. So for example, what is this state merging protocol when we only have one copy of the state? And this was worked out by these guys. And you can get something similar to what I use, but you have to change the entropies, right, by max entropy, mean entropies, and so on. So these things becomes harder doing it, but it still works kind of in the same way. So we use their results, and we also have to extend them a little bit to cover the situation we want. So, but the tricky part is really in this saturation of mutual information that I just mentioned. So the proof for the von Neumann case is very simple, right? As I mentioned, it's just subadditivity of entropy. For these max and mean entropies, it gets much more complicated, right? But because we have the intuition of this asymptotic, it still works in the end. So you just have to work more. And then this is how we do it. So I'm running out of time. Maybe change that. So okay. So just to conclude, so I show you that exponential decay of correlations in one dimension implies area law and implies that you have a good MPS parameterization. So again, this was a good way to show how how quantum information theory, like state merging and other things, they are useful for this kind of problems. There are many open questions that would be nice to know the answer. So for example, it would be nice to improve the dependence of the entropy of the correlation length, right? We have something exponential, but seems far from optimal. It would be very nice to have similar results in 2 dimensions or higher. We don't know how to do that. A more information theory problem maybe is to decide what happens in 2 dimensions for this problem of exponential decay of correlations, along without Hamiltonian and area law. Can we maybe create some more elaborate data hiding scheme in 2 dimensions and it will show that this result that I show in 1 dimension is not true? Maybe it's possible, but we don't know either. And if you want to look at our paper, there are more open problems there. So thank you for your attention.
Any questions? Enjoy. Bit early. No questions.
Wait.
I'm waiting. Okay, then thank you again.
Thank you.